So we have seen so far that for numerical attributes, if they have a few number of values, we could see them as categorical. If they have a large number of values, we have to split the data into intervals. So this is not simple. And the question is, can we consider mining quantitative association rules, which are the rules that contain numerical values in intervals, as a simple extension of mining categorical rules? And the answer is no. And the reason is that, first of all, there is an infinite search space. We don't have any more discrete number of values. In Boolean association rules, the a priori property allows to prune the search space efficiently, which means that if an item is not frequent, none of the more complex items, when you add items to it, will be frequent. But we do explore the whole search space of hypotheses, the whole lattice of item sets, which is impossible for quantitative association rules because there are an infinite way to represent these intervals in the data. The second problem is that the support confidence trade-off is actually choosing an interval that is quite sensitive to those measures. If the intervals are too small, then they won't have enough support. If the intervals are too large, then we are going to lack of confidence. So there is, in this case, a trade-off between finding a rule in which there is a balance between support and confidence. And of course, here in this case, we don't have any label to rely on to split the data into intervals. And we are just dealing with a completely unsupervised discretization of the numerical values. There have been different attempts to mine quantitative association rules, and this include discretization-based approaches, distribution-based approaches, and finally, optimization-based approaches. So for the discretization-based approach, we're going to perform a pre-processing step in which we just split the interval, the domain of the numerical features, into intervals. So we could use different strategies, use domain knowledge to have this cutoff points of the numerical features. And there have been several approaches to do that. We could also do some discretization based on clustering or interval merging. For example, if you have two intervals that actually don't have the support, you could merge them so as the final support of the final interval will be larger. So the problem with this approach is that it is univariate. You don't just look at how the features interact between each other. It can be sensitive to outliers. So if you have an outlier, it will be making the interval maybe the last intervals on the extreme sides of the domain being very large, and we lose a lot of information because of this univariability of the discretization and also the presence of outliers. The second approach to find association rules that have numerical attributes is based on the distribution of those attributes. So we're going to just include statistics of those features in the rule itself. So for example, this rule expresses that female are likely to have a height of with a mean of 168 and the weight with a mean of 68. So I'm going to plug in this standard deviation and mean of the features in the rule itself. There has been some attempts to do that. However, the form of the rule is restricted to some patterns on the left-hand side and some on the right-hand side to generate those kinds of rules. Optimization-based approach are actually the last line of research in mining quantitative association rules, in which numerical attributes or features are optimized rather than discretized. There have been different approaches to do that. One of them is inspired by image segmentation, in which we are going to find the intervals that optimize the gain of the rule rather than just calculating the support and confidence. So I'm going to restrict the rules into one or two numerical attributes at a time to perform that in this first line of research. The second line uses genetic algorithms to optimize the interval of the features in the attribute and uses some fitness function that takes into consideration the number of attributes and along with the amplitude and other parameters in the intervals. So, and it adopts actually an a priori-like algorithm to mine the set of association rules. The most recent approach include using half spaces to mine such rules, like a rule that says x1 is bigger than 1, then 0.5x3 plus 2.6x6 is bigger also than 100. But this approach, unfortunately, does not handle categorical attributes because of its aspect to find half spaces to mine such rules. A last approach is called QuantMiner that optimizes the gain of the rules templates using another genetic algorithm. So suppose you are combining in a rule two attributes, attribute 1 and 2, in which we have 2 intervals. So we're going to instantiate these intervals, and we're going to apply genetic algorithms and their operators to generate other rules. And the idea is to improve the rules along generations. So suppose you start with these 2 rules with some initial instantiations of the limits of the interval. If you do a crossover, you're going to generate new kinds of combinations of these intervals. You can also do a mutation in which you're going to reduce the size of the interval from the left-hand side or the right-hand side. So by doing so, you're going to generate generations and generations of rules based on the 2 operators of crossover and mutation. And you're going to keep those that have actually the best gain, which is a combination of the support and confidence that makes them balanced in the assessment of whether a rule is interesting or not. So let's take an example with the famous dataset from the machine learning repository, UCI iris dataset. So we have in iris 3 species of flowers described by the petal length, petal width, sepal length, and sepal width. And we want to find some rules that looks like that have some templates, such as have the special value on the left-hand side implies any combinations of the feature of the flower on the right-hand side. And you want to generate the support and the confidence of the rule. Okay, so applying something like quantminer to generate quantitative association rules will lead to rules that describe, let's say, species equals setosa. So setosa iris flowers, 23 of the flowers are actually having a petal width in 1/6 interval, a sepal width of 31-39, these are in millimeters, have a petal length of 10 to 19, and a sepal length in 46-54. And this rule is actually have a confidence of 70%. 70% of the flowers setosa has these combinations of feature values or feature intervals in the data. The species setosa with these features represent 23% of the data set. So you could do the same thing with having this versicolor on the left-hand side or virginica on the left-hand side. So these rules are generated basically by combining those intervals in several ways throughout many generations of rules. But we do start with the rule template that actually we want to fill by finding actually the best values of the left and the right of the intervals. If you want to play with a tool to mine association rules and quantitative association rules, you could play with this tool that's available on GitHub, and in which you're going to in which you have a simple process. So in the case of the iris dataset, we start with a table in which we have the examples and the features to associate. So this is the UCI iris dataset. The goal of the algorithm is to mine all interesting rules with respect to some pattern. So it's a 5-step wizard in which you select your data, you select the features you're interested in, and you ask the system to generate the rules for you. So the system actually allows you to open a dataset of feature values. So you have the features on the column, you have the examples on the rows. So this is the example of the iris dataset. That is one of the benchmarks in the tool. The tool is a set of 5 steps in which you choose your data attributes, choose your templates of rule that you're interested in, and then generate the rule. So here's an example of rule in which we have iris versicolor has a petal length in the interval 3.34.7, petal width of 1 to 1.5, and this is generated by the genetic algorithm in that you could observe the interval in the whole domain of each of the numerical features, and this rule is deemed interesting because it has a confidence of 82% and a support of 27.33% in the data set of 150 flowers. So these were association rules. I think it's an interesting line of research in the unsupervised setting of machine learning. So you could use it as an exploration tool when you have to understand better your data, see some clustering of your different items. Even if you interact with a domain expert, it's good to sit together and explore what data you have. It's an interesting tool to do as a pre-processing before as an exploration of your data before you even start and try other kinds of supervised and unsupervised machine learning methods. So I hope you found this useful. I will see you in the next lecture.